So we'll start with the brief, the title, I guess, development of a wearable interface with multimodal haptic feedback for intuitive VR-based teleoperation by Daria Trinitatova. Welcome, Daria. It's a pleasure to see you here. And in the doctoral program of engineering systems. So I will now go through the presentation of the jury members. And after this, we'll have the candidate presentation for 40 minutes or so. And then we'll have the Q&A by jury members and also from outside questions from the general audience if they wish. And then we'll have a word from the supervisor. And then the closed deliberation of the jury. And after this, after the discussion among the jury members, their decision and then outcome announcement with the candidate and everyone after, right? So let's start with the jury composition. Well, we'll start with myself as the chair. I'm the Dean of Education and full professor at Polytech, and joined Polytech in April 2014. I spent a number of years at École Polytechnique of Montreal, and from 2010 to 2014, I was president and CEO of the Consortium for Research and Innovation in Aerospace in Quebec, and extended it all across Canada from the Atlantic Ocean to the Pacific Ocean. And I'd been the director before of the Department of Mechanical Engineering at École Polytechnique in Montreal, and a professor at that institution since 1987. In terms of research, I started in vehicle dynamics, but spent most of my time and efforts in product lifecycle management or digital engineering. And based on this, created the company called Polyplan Technology, a spin-off from École Polytechnique, and we developed an innovative PLM solution, which was purchased by PTC of Boston, and now is implemented in 2,000 companies worldwide. So I'm a fellow of the Canadian Academy of Engineering and also of a few other organizations, including the Canadian Society for Mechanical Engineering and the Engineering Institute of Canada. That's it. Next one, please. Now, the second is Professor Tatiana Podlachikova. She's from Skoltech. She's associate professor at Skoltech and the director of the Skoltech Center for Digital Engineering. Tatiana joined Skoltech in 2013 and working previously at the Royal Observatory of Belgium, Laboratory of Astrophysics, and in Marseille and Space Research Institute of the Russian Academy of Sciences. So she has a broad experience in Europe and in Russia. Her scientific interests are related to solar and solar terrestrial physics, space weather. She developed a number of space weather services, including sunspot number, solar radio flux, and geomagnetic storm forecasting, prediction of arrival and high-speed solar wind stream at the Earth. She holds numerous awards, including International Alexander Tichevsky Medal for Space Weather and Space Climate in 2015, Belgium Best Professor of the Year in Belgium, and then the Best Professor of the Year at Skoltech in 2018, Best Professor of the Year at 2019 for lecturing, and the Best Professor of the Year 2020, Teaching Excellence for Skoltech. She got recognition for excellence in research, teaching, and impact and service to Skoltech and the wider community in 2022 and 2023. So welcome, Tatiana. Next member, Professor Andrei Somov, also associate professor at Skoltech and the head of the Intelligent Sensing Group. He joined Skoltech in 2017. He graduated from the Russian State Aviation Technical University, MATI, in Russia with an honors degree in electronics engineering, and Dr. Somov received his PhD in electronic engineering in 2009 from the University of Trento, Italy, having specialized in power management in wireless sensor networks under the supervision of Professor Roberto Passaroni. His research interests cover power management of WSN and Internet of Things devices, cognitive IoT, and associated proof of concept implementations. Dr. Somov has published more than 100 papers for peer-reviewed international journals and conferences. He's been general chair of the 6th International Conference on Sensor Systems and Software, the IoT 360 Summer School in the Internet of Things in 2014 and 2015. And Professor Somov holds a number of awards in the field of WSN and IoT, including Google IoT Technology Research Award in 2016 and the Best Paper Award at IEEE IOP in 2019. Welcome, Andre. Our external member now, Professor Fei Chen, is an assistant professor at the Chinese University of Hong Kong and the head of Collaborative and Versatile Robots Laboratory, Clover, with the Department of Mechanical Engineering and Automation Engineering and CUHK T-Stone Robotic Institute. Before joining CUHK, he was a researcher and founder of the Active Perception and Robot Interactive Learning Laboratory at Italian Institute of Technology, IIT. He has been acting as the PI for several EU and Italian national projects as EU FP7, EU 2020, and others. So he's been very, very active in Europe. His main research interest lies in robot mobile manipulation, robot grasping and manipulation, human-robot collaboration. Is an IEEE senior member. He's co-chair of the IEEE Robotics and Automation Society Technical Committee on Neuro-Robotic Systems. He also serves as associate editor for IEEE Transaction on Emergent Topics in Computational Intelligence and Frontiers in Neurorobotics. Welcome to the jury, Professor Shen. Next member, please, Professor Yuha Jin is an assistant professor at the School of Science and Engineering at the Chinese University of Hong Kong. Professor Yuha Jin received his BSc in Applied Physics, MEng in Optical Engineering, and a PhD in Optical Engineering from Beijing Tech University of Technology in 2010, 2013, and 2017, respectively. Following this, he spent 2 years as a postdoctoral associate in HCI Engineering Group at MIT, CSAIL Computer Science and Artificial Intelligence Laboratory from 2018 to 2020. Before joining CUHK, Shenzhen as a tenure-track assistant professor in School of Science and Engineering, SSE. He also served as a visiting scholar at the School of Computing Science at Simon Fraser University in Canada, and as the CTO of Tinted Technology, Inc. in Italy. His research interests include human-computer interaction, optical engineering, personal fabrication, visualization technologies, art, and design. For his research achievement, Dr. Jin received the Best Paper Award and the Best Talk Award at ACM UIST 219 and was also awarded a DCE Expo Special Prize at SIGGRAPH 2020. Welcome, Professor Jin. So, now the next one is Supervisor. He's Professor Dimitri Tetsiroukou, Associate Professor with the Center of Digital Engineering at Skoltech, and he's head of the Intelligent Space Robotics Laboratory. Dimitri Tetsiroukou received his PhD degree in Information Science and Technology from the University of Tokyo, Professor Susumi Tachi Laboratory in Japan in 2007. From 2007 to 2009, he was a GSPS postdoctoral fellow at the University of Tokyo. He worked as assistant professor at the Electronics Inspire Interdisciplinary Research Institute, Toyohashi University of Technology from 2010 to 2014. His research interests include autonomous robots, swarm of drones, human-robot interaction, wearable haptics and tactile displays, teleexistence, affective haptics, virtual and augmented reality, and artificial intelligence. In 2023, he was awarded by Elsevier Scopus the rank of top 2% of the world's most cited researchers. Professor Tetsiroukou received such prestigious awards as Best Paper Award, Asia Haptics 2022, finalists of Franklin V. Taylor Memorial Award, IEEE SMC 2021, Best Demonstration Award, ACM SIGGRAPH Asia 219, Best Demonstration Award, Bronze Prize, Asia Haptics 218, Laval Virtual Awards, ACM SIGGRAPH 216, and Best Paper Award, ACM Augmented Human 2010. So welcome, Dimitri, with us. Now the PhD candidate. This is her day. Daria Trinitatova received her BSc in Applied Mathematics and Physics from the Moscow Institute of Physics and Technology, MIPT, and an MSc degree with honors in Information System and Technologies from Skoltech. Her research interests include haptics, virtual reality, teleoperation, human-computer and human-robot interaction, digital twins and simulation environments for robotic systems. She has published research papers in the field of haptic interfaces, virtual reality, teleoperation of robotic systems in the proceedings of prestigious conferences such as World Haptics Conference, IEEE SMC, IEEE Case and Journals of IEEE Transaction in Haptics, and IEEE Robotics and Automation Letters. During her PhD study, Daria received the Outstanding Reviewer Award at IEEE Haptics Symposium 2022 and won a grant from the Russian Foundation for Basic Research for postgraduate students to support her PhD research. So, pleasure to have you with us, Daria, and we will give you the floor for your presentation now for a maximum of 40 minutes, and we'll listen to you carefully. And after this, we'll have questions and comments for sure. Daria, it's all yours.
Thank you. So, good afternoon, dear committee. It's a pleasure to see you here, and also thank the committee members that that follow us online today. And now it's my pleasure to start my presentations about my PhD study that is devoted to the development of a wearable interface with multimodal haptic feedback for intuitive VR-based teleoperation. With the rapid development of artificial intelligence, many robotic systems are currently become autonomous without need of human intervention. However, still there is a need of presence of the operator in order to create a more adjustable systems with a non-determined scenario when precise and dexterous manipulations of objects is required. Deliberation plays an important role to improve the human-robot interaction by extending the human capabilities, improving the safety of robot operations, and facilitate collaboration between human and robots in various domains. During teleoperation tasks, the visual feedback of the operator is usually overloaded. That will lead to high cognitive loads. By applying virtual reality, it's possible to create a more intuitive and natural interfaces that immerse users in 3D environment and allows to view and interact with robots. In addition, the visual channel for the operator can be augmented by simulating the sensations of touch. Thus, haptic technologies can improve the perceptions of remote environment and provide the information about the properties of objects being manipulated. Currently, the most interfaces for robotic teleoperations are not very intuitive, which lead to significant cognitive loads when controlling a robot. Pure video-based approaches for teleoperation contains a series of limitations, such as a limited field of view, camera resolution, and bad light conditions, which affects to the immersion of the user during teleoperation and also the level of user awareness about the remote environment. In addition, to provide delicate and dexterous object handling, it's needed to provide the operator with real-time information about the grasping state. Using both the advantages of virtual reality and haptic technologies, it's possible to improve the quality of teleoperation and increase the level of user involvement during teleoperation tasks. Now let's briefly consider the state-of-the-art works in the areas of haptics and control interfaces for teleoperation. So various wearable devices for the hand were proposed by researchers that can provide haptic feedback in form of kinesthetic feedback, that is strong forces applied to the hand, and cutaneous feedback that is represented by vibrotactile, electrotactile, and thermotactile feedback. The popular form factor for designing wearable haptic displays include design of exoskeleton's glove that was proposed by Michikawa. These devices provide kinesthetic feedback to the user's hand and allows rendering a stiffness of VR objects during grasping. Another popular approach is designing wearable interfaces for the fingertips, as the fingertips has the most sensitive areas at the hand. For example, Lee proposed a multi-finger haptic display that can render shear and normal forces to the fingertips. And another approach combines kinesthetic and cutaneous feedback in one device. For example, Sun and Park proposed a glove that can present a finger force feedback with a combination of cutaneous feedback to the palm. Recently, there is an increase of using virtual reality for robotics teleoperation domain. For example, Wonsik proposed a telemanipulation virtual reality interface that allows users to choose the convenient viewpoint during teleoperation process, and also it creates visualizations of preliminary trajectory during robot operations. The second example is proposed by the researchers from Italian Institute of Technology. It's a vicarious VR interface that represents a hybrid environment that contains VR with digital twin of the robot that is augmented with point cloud reconstructions from the remote environment. And also, VR environment is augmented with real-time video stream from the remote surroundings from the robot. And the third example is a recent work. It's an open source framework, OpenTeach, that allows users to easily interact with any types of robot by using just a VR headset and just natural hand gestures. As was mentioned before, haptic feedback can provide many advantages during teleoperation process. And currently, a lot of researchers study how to apply an effective combination of different tactile stimuli to the user's hand to improve the teleoperation process. For example, Chinella proposed a wearable interface for the forearm that can provide a skin scratch feedback to assist the user during navigation tasks. The second example is application of a combination of kinesthetic and cutaneous feedback that provided using a wearable haptic device during telemanipulation tasks. And similarly, Agrave proposed also to use a combination of kinesthetic feedback that is proposed by grounded omega-6 haptic device and the vibrotactile feedback that is provided, that is generated through a wristband on the user's hand to improve and to assist the operator during flexible needles insertion tasks. To sum up, from the literature review, I defined a research gap for the current work. So there is a lack of an effective visual tactile interface for intuitive and natural teleoperation for a user, which can provide a real-time feedback during teleoperation. As a solution, I propose to combine a VR system with a wearable haptic interface that can provide a wide range of haptic feedback to improve the quality of teleoperation and increase the level of user involvement during the teleoperation tasks. The term wearable haptic interface combines the haptic displays that can provide the user with haptic feedback and a tracking module that can represent the hand position during the teleoperation. Also, I defined 3 research questions for my research, and the first is devoted to the application of wearable haptic interface to improve the user performance during manipulation process. Wearable devices is an appropriate area to apply haptic technologies because they do not restrict the operator's movement and provide a large workspace during operation. Also, the recent advancement of haptic technologies allows to design devices that can provide a high fidelity haptic feedback to the user's hand. By creating a wearable haptic interface, it's possible to improve the precision of robot control and increase the naturalness for the operation. The second research question is what benefits could multimodal haptic feedback provide to assist the user during the teleoperation process? So application of multimodal haptic feedback can increase the safety during operations by providing different alerts about possible hazards during operation process. Besides, it could be achieved a better spatial temporal coordinations during robot operations. And finally, multimodal haptic feedback can significantly improve the perceptions of object properties during telemanipulation tasks. And the third research question is related to the application of VR-based system to improve the intuitiveness and increase the level of naturalness during robot control. So VR technologies allows to create highly immersive environments and to improve the user perception of remote surroundings around the robot. Also, VR system can be used for training and simulation before performing real teleoperation tasks with real robots. And the main goal for the current research work is to develop and study the impact of a wearable haptic interface and a VR system to improve the quality of teleoperation. To achieve this goal, it's necessary, firstly, to develop a wearable haptic interface that can provide a wide range of feedback to the hand, and of course, evaluate the performance of this interface by conducting different user study on the perception of multimodal tactile stimuli provided to the hand. Also, it's needed to develop a VR-based framework for robotic teleoperation and integrate this framework with tactile control haptic loop to assist the operator. Besides, it's needed to propose an effective haptic guidance approach, for example, to assist the operator during navigation tasks. And finally, it's needed to evaluate the developed system on the user performance during a series of teleoperation tasks. And the current thesis contains 6 chapters, so the first and the second chapter was already mentioned during these presentations. The third chapter is devoted to the development of the wearable haptic interface with multimodal haptic feedback. The fourth chapter will describe the VR-based framework for robotic teleoperation. The fifth chapter will be devoted to the experimental evaluation of the haptic guidance approach during robotic teleoperation. And the last chapter concludes this work and highlights the direction for the future work. Now let's consider the development of a wearable haptic interface for delivering multimodal haptic feedback for the user's hand. The concept of a modular wearable haptic interface consists of developing a system that combines haptic displays that can provide tactile stimuli both to the palm and to the finger pads, and a hand tracking module that can represent the hand position and finger movements in virtual environment. As the first module for this interface, I developed a wearable haptic display for the palm, Delta Touch. It has 3 degrees of freedom, and the mechanism is based on the inverted delta structure, which is proposed to achieve a lightweight and compact structure and to achieve a fast movement of end effector along the palm. The designed device can produce a 3D force vector at any point of the palm with different levels of pressure. Delta Touch display is designed to provide a multimodal stimuli to the user's palm. In terms of contact and pressure, also it can provide skin stretch feedback, which is a sliding movement of end effector along the skin of the palm. Also, it's possible to provide a vibrotactile and thermal feedback by applying additional modules for the moving platform of the device. The performance of the developed display was evaluated in a series of user studies on recognition of different tactile stimuli that was provided to the palm. And the first study was devoted to the discrimination of the multimodal tactile stimuli. So it was designed as 13 special contact points that was delivered across the workspace of the device. During the contact state with the skin, it was also provided one of 3 developed vibrotactile patterns. So according to the experimental results, the mean percentage of recognitions for the contact patterns comprised about 70%, and the most recognizable areas at the palm were located at the center and across the outer diameter of the workspace of device. And the mean percentage of the correct answers for recognized vibrotactile patterns comprised around 90%. The second user study was focused on the discriminations of different skin stretch patterns delivered to the user's hand. So it was designed 8 skin stretch patterns that differs in the movement of end effector with the increment of 45 degrees. And according to the obtained result, every pattern was highly distinctive, and the mean percentage of the correct answer comprised about 80%. While obtaining the good recognition rates, it was decided to apply this skin stretch pattern further to assist the operator during teleoperation process. As the second model for the wearable interface, it was designed a haptic display that can provide the 3D force vectors to the finger pad. The design of the display is also based on the inverted delta structure. And this display can provide a multimodal stimulus such as contact and pressure, vibration, and slippage to the finger pad. The performance of the designed display also was evaluated through a 2-stage user study on the recognition of static and dynamic patterns delivered to the finger pad. So the first part of the experiment conducted included the discriminations of 9 special contact point that was delivered to the index finger of the users. And the mean percentage of the correct answer comprised 74%. And the most recognizable points on the fingerpad were located at the center, up and down of the workspace of the device. During the second user study, it was designed 8 skin stretch patterns that was delivered to the fingerpad. Similarly, that was done for the palm. And for this experiment, it was obtained the mean percentage of the correct answers, about 84%. And the most recognizable skin stretch patterns were right direction and down. So with obtained result, we can conclude that both designed devices can provide a highly distinctive static and dynamic patterns that could be used to assist the operator in teleoperation and telemanipulation tasks. As a third model for the wearable interface, it was designed a hand tracking glove that can present the rotation of the hand in virtual environment as well as a finger movement. So the prototype consists of the ESP microcontroller, a flex sensor with 1 degree of freedom that can represent the bending of the finger, and a tilt sensor for representing the rotation of the wrist. In addition, it was added 5 vibration motors to the glove to provide a simple haptic feedback in the form of different vibrotactile patterns during the interactions with VR objects. Now let's consider the concept of VR-based framework for robotic teleoperation. The proposed system consists of your 3 robotic arm that is equipped with a 2-finger gripper with embedded tactile sensors and RGBD camera for recognizing the remote environment. At the operator side, it was developed a control interface that is based on Unity engine that combines the different models such as visual feedback model, communication interface, data processing interface, and a controller model that is responsible for providing tactile feedback to the user and mapping input stimulus to robot control. As for visual feedback, it's proposed to use a hybrid environment that combines a simplified version of remote environment in virtual reality with a digital twin of the robot, which is augmented with the real-time video stream from the remote environment. In addition, it's possible to augment virtual environment with the renders of object phony manipulations that are detected using a single depth camera attached to the robot. Using the proposed VR-based framework, it's proposed an intuitive approach for robot control using a wearable interface with 2 control schemes, position control and velocity control. For both schemes, the operator hand position and orientation, it's mapped in case of position control directly to the position and orientation of 2 center point of the robot. And in case of velocity control, the position and orientations of user's hand set the direction and velocity of robot movement. Now let's consider the experimental evaluation of the haptic guidance approach that uses multimodal haptic feedback during robotic teleoperation tasks. So the robot is controlled with the V-Delta glove wearable interface that combines a hand tracking module and a palm warm haptic display that can provide cutaneous feedback to the palm. For the teleoperation system, it was designed a virtual environment with digital twin of the robot that represents all the physics of real-world robot. The haptic guidance approach is aimed to increase the level of special coordinations of the user during teleoperation process in the following way. So during the robot motion in horizontal plane, the user is provided with the skin stretch patterns on the palm that delivered by a palm worn display. During the robot movement in the vertical plane, a vibrotactile pattern is delivered to the users by using a hand tracking glove. And during the robot movement in 3D space, the combinations of both types of feedback is provided. To evaluate the performance of the developed wearable haptic interface, it was conducted a comparative user study experiment on the teleoperation of robot in the domain of path-following task. So it was designed as 3 trajectories for robot movement in 3D space. Also, it was chosen 3 different interfaces to compare with the developed Delta glove interface. That represents teach pendant is the baseline interface for control of your robot. The next one is Omega 7 desktop haptic device that's often used for the teleoperation domain. And the third one is a VR controller, which is a low-cost solution that is also often applied for different VR-based interfaces. To measure the user performance during teleoperation tasks, it was decided to measure the task execution time and accuracy of path following. In addition, after completing the tasks, users were provided with 2 questionnaires to evaluate the subjective measures. In terms of NASA task load index questionnaire that measures different loads during operations such as physical demand, mental demand, efforts of the user. And the second questionnaire is evaluates the user experience of interacting with control interfaces. So here is a demonstration of teleoperation experiment. So using teach pendant interface, it's possible to control a robot using a buttons through graphical user interface that allows the robot movement along one axis simultaneously. The second interface is Omega 7. It's allowed to control the robot using moving the handle of the device and provide a direction and velocity for the robot movement. Also, this device can provide a kinesthetic feedback during teleoperation. The third interface is VR controller. With this controller, the hand movements in 3D space are mapped for input signals for the robot control. And the last interface is the Delta glove haptic interface. It has a similar approach for controlling the robot using the hand movement in 3D space, but with this interface, the user is assisted during navigation tasks by providing cutaneous feedback during operation. So let's consider the experimental results that we obtained. If we will consider task execution time, we can conclude that the time of operation was the least in case of using the baseline interface, which is teach pendant. If we will consider accuracy of path following, we can conclude that 3 node baseline interfaces, such as Omega 7 haptic device, VR controller, and developed Delta glove haptic interface showed a similar performance. And with the developed interface, the average error of trajectory following comprised around 5 millimeters. Now let's consider the results of the NASA TLX questionnaire. So the results show that the Delta glove interface showed comparable characteristics with another haptic interface, which is Omega 7. If we will consider only wearable interfaces, V-Delta Glove outreach VR controller in terms of mental demand, user effort, and performance during teleoperation. So the second subjective evaluations comprised the evaluation in terms of 6 attributes. And the Delta Glove interface outreach, teach pendant, and Vive controllers in terms of attractiveness, dependability, stimulation, and novelty. Also, the Delta Glove interface outreach Omega 7 haptic interface in terms of user evaluations for all attributes. Now let's sum up the contributions for this research and directions for the future work. As a result of the conducted research, it was developed a novel wearable interface which can provide a wide range of tactile feedback to the user's hand. The conducted user studies showed a high recognition rates of providing recognition both static and dynamic patterns delivered to the palm and to the finger pads, which could be used to assist the operator during teleoperation. The presented VR-based framework, combining visual interface, communication interface, robotic controller, and haptic loop, is aimed to increase the level of naturalness during robot control. Also, it was proposed a novel haptic guidance approach, representing a combination of skin stretch feedback delivered to the palm of the user and vibrotactile feedback delivered to the finger pads. And during the teleoperation study, the developed V-Delta Glove interface showed comparable characteristics with the commercial available Omega 7 desktop haptic device and outreach the performance of VR controller. Besides, the Delta Glove interface showed superior evaluation in terms of user experience over other interfaces. As for direction of future work, of course, I highlight the further development of the design of the Delta Glove interface in terms of ergonomics and size. Also, it's needed to further explore the ethics of applying multimodal feedback for assisting operators during teleoperation. As the second step, I'm going to develop a robotic perception system that can recognize the different object properties during telemanipulations, such as, for example, applied pressure to the object, the level of object deformation, and so on. And the most important part is that using the developed VR system, we can create an effective tool for the dataset collection for the application in the imitation learning domain. So by applying simulated environment, it's possible to collect the data such as robot trajectories, simulated data from the camera views, and tactile sensors to teach the robot to perform a complex autonomous operations from operator demonstrations. So during my PhD study, I published 2 journal papers in such prestigious journals such as IEEE Transactions and Haptics and IEEE Robotics and Automation Letters, as well as I published 9 peer-review conference papers in such conferences like World Haptics Conference, IEEE CASE, IEEE SMC, and SIGGRAPH Asia. Also, during my study, I won a grant for the Russian Foundation for Basic Research for postgraduate students on the topic of research on the influence of a wearable tactile interface on the immersion of perception in virtual reality. Also, I want to thank my supervisor to support me during this long way of study. Also, I want to thank all of PhD jury members for your valuable comments that was delivered that helped me to improve the final thesis work. Besides, I want to thank all the students that participated in the conducted user studies and provided me valuable feedback to improve the developed technologies. And especially, I want to thank several colleagues that I'm fortunate to collaborate with and have joint projects during my study. So thank you for your attention. I'm ready for the questions.
Thank you very much, Daria. We will now go into the question period, and we'll start with our external jury members. We'll start with Professor Chen, please. So if you have any questions, please go ahead.
Okay, thank you, Chair. So first of all, roughly like how much time for me? 10 minutes or something?
Oh, you have as much time as you'd like.
Oh, okay. Thank you. Maybe I can start with a few simple questions and maybe leave out time to other jury members. So thank you, Dario, for your for the presentation or your research work during your PhD study. And so I went through your thesis, and I also noticed that a lot of my comments have been addressed by you during the revision, and I appreciate that. So back to the presentation today, I have a few comments or questions for you. So first of all, I fully understand your motivation about your research. You would like to tackle the gap of the issues of this problem, and so I understand roughly your research could be roughly two parts. One part about the design of the haptical device, tactile device for the tactile sensing. And the second is about integration with robot teleoperation for some application-oriented technology development. So regarding the part one, so I noticed that you emphasize the issues about the intuitive and natural feeling about the using the haptical device. And I noticed in your research work, so you had designed like three pieces of the haptic device, one for the palm, one for the finger, and a third one is about the glove. So, which seems to me that the emphasize or more detailed analysis of the what kind of tactile signals, which are very important for such an intuitive and natural feeling, is not very explicitly explained or explored in the presentation, and how they drive the design of the user case study, user case experiments are not very clear to me. So can you give some more discussion or explanation regarding this part?
Yes. So thank you for your question. Lena, could you show up the presentation? I will find the necessary slide. Okay. So we will consider the assisting of users in terms of providing feedback for fingerpads. It's possible to recreate the feeling of objects that was grabbed by the robotic gripper in terms of contact points stimulated and the finger pad as it's stimulated in the robotic gripper. And in order to understand if user will clearly distinct like the position of stimulated point or the direction, for example, of sliding the objects on the finger pads, we conducted a user study to explore if the perception of the finger pads is enough to recognize different stimulation points and different directions. Similarly for the user's palm. In case of palm, the patterns was used to navigate the operator during the teleoperations. And in order to effectively assist during navigations, the device should provide a highly distinctive, for example, directions stimulated on the palm. And in our case, it was considered like a skin stretch patterns that was delivered to the palm area. And we obtained that all the designed patterns had a highly distinctive recognitions rates. That means that user will be effectively recognize the stimuli that is aimed to help him or her during teleoperation. I hope that I answer your question.
You also, oh, okay. So, yeah, yes, I noticed that this content. It's so my question is more about from the user point of view, from people's point of view, what kind of important tactile sensors signals are needed from the hand, like how from the palm, from the fingertip, and what kind of combination of both signals could be used to improve the intuitive or something. So this is so currently your organization of this study is more about separate style. I'm not sure if I interpret it in the wrong way, but it seems one is for palm, one is for the fingertip, and also you have a third one is about the glove. And later, also noticing the second part about the experiment with the robot, it seems to me only used a fingertip signal, right, for the robot part. Maybe we can talk about it later. But probably I think you can consider adding one small discussion about why what kind of from comparing from the previous work, what you discovered which is missing, that you would like to emphasize the research that you want to get a signal from palm and from finger to use both of them combined can be used to improve the user the performance, the gap, okay, to resolve the problems that you would like to tackle. So that's my feeling regarding this part. Yeah. Also regarding the fingertip part, it seems to me you don't have video, right? Do you have a video for showing the finger? You have a good video showing that palm sensor device, but regarding the fingertip, do you have a video?
Sorry, I don't have a video for the fingerpad device.
Yeah, that's what I observed. Yeah. So this is my first comment regarding this part one. I think there's some hidden information, which is better. Maybe you can summarize into a more explicit point of view that why they are important to be used, and then you design devices to capture them would be very convincing. Yeah, that's my first feeling. Yeah. The second part about the teleoperation of the robot, and I noticed that you had a good comparison study about the control schemes using different kinds of teleoperating interface in the pitch pendant, in the Omega device, and also your designed haptic device. I noticed that you only used trajectory tracking as experiment, which I'm not so sure the tactile signal plays a very major role in such experiment. Do you have any comment on this?
Yes, so actually, the evaluation of the tactile patterns to assist the user during navigation tasks was like a first step of the conducting research. And firstly, I'm going to conduct a study that will include also the stimulation of finger pads during an already telemanipulation process to explore how we can help the user to feel the properties, for example, of objects, and to increase the effectiveness of manipulations of remote objects. But now it's this step is only on the stage of preparation.
Yeah, okay, yeah, this is exactly what I was expecting, right? So I thought you would like to use a device to help with the tactile feeling of the objects in the virtual environment or in the real environment or something. Yeah, okay. Yeah, so also I noticed that back to this research, you have several different experiments set up, but it seems to me the evaluation from the quantitatively is missing, like how even from the trajectory point tracking point of view, if you can show how good they are for you to track the trajectory, how good this kind of haptic based on interface can be used in future for feeling
So for the measured,
conflict. Sorry, what did you say?
Sorry, we lost you for a little while there. Could you repeat your question? Because we lost you for about 10, 15 seconds in the middle.
Oh, okay, sorry. So am I clear now?
Yes, you are. We can hear you well now.
Okay, so Daria, my question is that you have, it seems to me, do you have any quantitative analysis of the tracking accuracy of something for these experiments? So you only show the video of the experiment, but you didn't show the data. Yeah.
so as it was developed a virtual environment for robot teleoperations, with this environment, we write the data from robot movement, such as like position and orientation of the tool center point, and time of operation. And that comprised like quantitative metrics for this experiment. Like the accuracy of path following that was measured using virtual environment, and task execution time.
Okay, see, I noticed this. Yeah, okay. Yeah, so maybe I can stop here. Yeah, if I have some more questions, I can add later. Yes, thank you, Daria, for your answer.
Thank you.
Yes. And yeah, you're welcome to ask some questions after, but I have a question for you. Are you satisfied with your thesis?
Yes. Okay.
Okay.
Yeah.
Thank you very much. Now we'll go with Professor Jin with your questions and comments. Please go ahead.
Okay, it's my turn now. So first and foremost, thank you so much
Yes,
for
go
your invitation. You know, I have reviewed the thesis of Daria, and I'm impressed by the depth of this research and the innovative approach taken. I think this research is very meaningful. It brings me back to the days when I watched those Japanese animes. I'm a big fan of those animes. Like, how could a human being drive those huge super robots? Like, first of all, you should see the views of those robots, and secondly, you should control those robots with some controllers inside those robots. So I feel I find it both exciting and timely. But you know, besides that, you know, as we proceed, I look forward to a productive discussion about your research methods, findings, and the broader impact of your work. So because this is your defense today, I'm not be that kind of because I prepared 4 questions for you. Some of them may be a bit critical, but some of them may be easy. My first question is about your technical stuff and your methodologies. You know, I'm actually very curious about your design choices. So my first question is, what were the critical factors that influenced your design decisions for the V-Delta glove, and particularly, you know, regarding the structure, selection of the sensors and actuators? Is there anything inspired you for the design of this device?
So thank you for your question. So first of all, I had a task to create an effective display that can provide a feedback on different parts of the hand. And for the particular study, it was chosen a palm area and fingertips because this area are the most sensitive for the perception of tactile stimuli. Secondly, while reviewing like a lot of state-of-the-art work, I defined that we need to provide as much as possible combinations of different tactile stimuli to provide like a fully immersive environment for the user. And like a mechatronic structure seemed to be like ideal case to apply for the construction of devices. Particularly like inverted delta structure allows to provide a precise and fast movement of the end effector that can deliver different stimuli with super fast like velocities. Also, this particular structure is super compact if you will consider like the number of degrees of freedom that it can represent. And the light of the structures is also low, which also could be like improved in terms of applying smaller servo motors, for example, and applied more light materials during prototyping of the device.
Okay. That sounds good. And I think in your thesis, this is my suggestion. Maybe you'd better to record your thoughts and your design trends, you know, in your thesis too, because once you publish your thesis, your PhD thesis online, when you became famous, when you become famous in the future, maybe you became a professor in the future, there will be a lot of you know, readers. They will review your thesis, right? And they will get inspirations from your thesis. And they maybe, I think such a kind of record in the aspect of design could have some inspirations for those new reviewers of your thesis. So this is my first question. And my second question is a little bit critical. You know, in the thesis information you provided, there was no any specific mention about the research focusing on the latency between visual and haptic feedback in the context of the developed system. I believe this aspect is pretty important. You know, addressing latency, you know, the delay between visual and haptic feedback is pretty critical for ensuring some effectiveness in in those teleoperation systems, especially where real-time feedback is pretty important for operations. For those medical robots, like for gaming, and for remote driving, and some other operations, etc., etc. So could you please explain how you think about this and why you didn't do such kind of research in your previous work?
Yes, thank you for your question. Actually, for this work,
Yeah.
the latency wasn't measured strictly. That could be considered as a limitation of the current research. It was measured only like empirically using multiple testing and during user experience deliberation. So for the worst case, we had a latency of about a half second between like the visual channel and the haptic channel. And I suppose that the most like part of the delay is related to the communication interface, because now as for communication between like an application, their application and haptic displays, it's used Bluetooth connection, which is not the most reliable communication that can be used. Maybe we can consider to use a radio frequency interfaces to improve the speed of data transfer.
Yeah, that's it. Okay. I think yeah. Your question is it doesn't matter so much, but it would be better if you have a discussion part, maybe in your future work, this is like yeah, I do believe if I use your system like to drive a car by a robot, like a remote driving, if I see some risk ahead of me, I want to avoid, but the latency could stop me, and yeah, I mean, if the latency is there, so maybe I would crash some barrier ahead of me after I realize it. So that would be horrible. So this is what I mean. Yeah, I think that such a kind of discussion in your thesis should be helpful for those new readers if they notice that problem. That's my opinion. And my third question is, have you ever considered about to design some multi-point stimulation for your glove? Like, the current design of your V-Dirt Touch provides only a single point stimulation, which will effective, but I believe it could be enhanced to offer multi-point stimulation. Do you have any ideas on that?
Yes, thank you for your suggestion. Of course, we were thinking about how to like improve the performance of device. The problem with the multi-point stimulation is that in order to create multi-degrees of freedom, stimulation of each point, we need to apply a lot of actuators that will significantly increase the weight of the whole structures, and it will most probably decrease the ergonomics of device. Of course, we can achieve this kind of stimulation by applying electrotactile stimulation, because like a current technological progress in creation of electrotactile displays allows us to produce high fidelity stimulations with multi-point like achievement on the finger pads, or maybe even for the palm area. So maybe
Mhm.
the future step we'll consider to adding some flexible displays that can provide electrostimulation to the different points of the skin.
Mm. Yeah, that would be a good idea, you know. To my opinion, the mechanism, the mechanical development of this device is pretty tough. Like you need to design a lot of mechanical structures, but as you suggested, maybe some new electrical shock material would be a good way, yeah, to improve your device. Okay. And my first question is about you know, do you have any plans to integrate other sensory feedback mechanisms? You know, just like by incorporating with other additional sensors, operators, which would let your new device maybe could not only see and feel, you know, but also hear, smell, and potentially taste the environment in which the robot operates. I think that would be super awesome. So do you have any other ideas on how to improve it?
Yes, thank you. It's really interesting suggestion. So if we will work towards creation a truly teleexistent system, of course, we need to represent not only like the visual part for the user and like tactile channel, but
Right.
we can create some devices that can like produce some smells in virtual environment by like simple controllers. And also it's possible, of course, to reproduce some sound effects in order to assist the user,
Right.
like during manipulation. Maybe it's possible to represent like the sound of texture interaction, that like the texture of the object is rough or was it like soft or rigid. It will, I think, like significantly increase the level of immersion for the user.
Good. All right. So that's all my questions. Let's conclude my Q&A session here. And yeah.
Thank you very much,
Thank you.
Professor Jin, for your
My pleasure.
questions and comments. And I have a question for you. Are you satisfied with the corrections and comments and answers that you received from Daria today? Does that mean everything is fine? Okay. Thank you very much.
Yes, everything's fine.
Okay. All right. So we will now go to Professor Somov with his questions and comments. Please, Andrei.
Daria, thank you for your presentation, for your PhD thesis. Well, actually, I've had a similar question to Professor Jin. Just was wondering whether there will be opportunity to add a sort of technologies, I mean, in terms of cognition, so that the user and your haptic systems could recognize context in order to familiarize the user with objects he tries to touch. Because I've seen that you plan deep learning application in your future work, but it could be a bit heavy. So maybe any other ideas in terms of sensing of context and objects and user support?
Actually, like another idea to like improve the user awareness during object deliberations is like apply large language models that can be used to stimulate, like to produce a different kinds of stimuli depending on the like user message. For example, user can say, like when he is interacting with virtual reality, I want to touch some soft object, and it will be like created a controller that will like create an input signals for the haptic displays to represent like the compliance of objects.
Yeah, all right, thank you. And apart from technical questions, so as a person with PhD, we should also have a sort of broad thinking, I would say. So how do you think, what would be the impact of your thesis, of your technologies you developed for society, for science? So what we should expect in the future?
So I hope that the current work will encourage like the young scientists and students to continue the work on studying of how we can effectively represent different types of tactile stimulations, maybe by using novel like materials technologies, not by just constructing some mechanical devices, by also like applying, as I mentioned before, some flexible materials with electrotactile stimulations or shape memory alloys to create truly like advanced haptic gloves, for example, that will have huge ergonomics and a low weight and will like represent like just a simple glove without different structures from mechanical points of view.
Okay, thank you. Have no questions. I'm satisfied with the answers.
Satisfied,
And
okay.
no corrections, yeah.
Okay. Thank you very much, Professor Somov. Now we'll now go to Professor Podlachikova with her questions and comments.
Yeah, thank you very much for very interesting work. I have a question when about again like a follow-up question about naturalness and intuitiveness. With a human brain, this is quite simple, but the most simple things are the most complex ones from the point of view when we try to formalize it with scientific language. And the question to you, what are the measures of this naturalness and intuitiveness? How you can measure it that to try to improve it? It was your, I think, your goal number 3. Can you give some formal criteria for that?
So first of all, of course, it's like a subjective measure, like not objective. And so for my area of research, actually, like researchers created a lot of subjective questionnaire that try to evaluate the user experience in terms of different aspects. For example, it could like contain the question, so how natural was the interaction with the objects, like evaluated from 1 to 5. Of course, it's like not objective measure, but using this even using these questionnaires, we can conclude that okay, like users highly evaluated the perception, and it means that we somehow improved like the immersion and intuitiveness.
But how can you be sure that your subjective approach works? What are criteria for that?
The happiness of the user.
Happiness?
Happiness. Yes, if it's happy with this device, if it's like can provide enough level of perception, it's already a success.
And how do you measure happiness?
It's a philosophical question. So actually,
let's not speak about like future, but how did you do it in your work? Like, let's be pragmatic. How did you get this satisfaction level?
Yeah, so like I applied like 2 standard questionnaires. The one is like an STLX that measures different loads during, like for the user during operation F, and like the less the load, the better the system. So like obtaining results, we can conclude that we improved like the user performance and the evaluation.
Yeah, this is, you see, already come with some objective criteria to decrease the load, right? Yeah. What else?
Also, we can measure, like, in terms of like robotic teleoperation, of course, we can measure the, as it was done actually, the accuracy of robot operation. Also, it could be measured like the numbers of successful tries during operations. How easy was for the user to like conduct this particular task? Was he successful or not during the operation? And of course, like a time of operation is also an important metrics, but not for all tasks. For example, if we want to create a super accurate like positioning of robots, we can increase the time of operation, but with increasing the accuracy. And if the user, for example, will try to operate the robot really fast, it can lead to decreasing the overall like accuracies.
And can you give a recommendation to the user which speed should be used? Like what would be optimal to achieve this naturalness and intuitiveness?
I think it depends on the user. If we have a task to have like a precise movement, of course, we will not consider like the time as a success factor. If we have a task to make some manipulations as fast as possible, so like the time will be the main criteria for this experiment.
Okay, thank you very much. And I'm satisfied with all the questions and answers.
Okay, thank you very much. I have a few questions for you, Daria. You did a lot of work with a lot of people. You did develop a number of devices and you tested them. When I looked, that was an impressive series of tests there with a number of people. In terms of learning to use the device, what do you think are the most important? I'm not saying, okay, once you've learned, okay, you can do something, but the learning, which one was the most difficult to learn for the people to adapt to?
It's a tough question.
If you go back in your memory and look and remember what the people did try, what do you think is the most difficult to learn to adapt to?
So I think during our evaluation studies, the most difficult parts was that the time of conducting the study is very long, and the user can have a decrease in perception of different patterns that can lead to like the decrease of the overall performance. And I tried to make some breaks between like different sessions, and every time I ask like the user, so if it's comfortable for you to like to feel this device, or did you like, are you sure that you feel all the contacts well or not? And like for these purposes, I also tried to make some like in-person calibrations before every sessions, in order to like make the performance of the users the best.
Okay, thank you very much. So from what you answer, I remember, I understand that it takes a lot of concentration and you can get tired doing it, right?
Because the user should not rely like on the visual feedback, because the device always like hidden from the view, and on show it should just rely on some tactile perception. And for some users, it's not super intuitive to use this channel like in our life.
Okay, yeah, that's quite a learning experience. You're right. I have my last question is, you develop a number of devices and you tried many things. What do you think is the most promising, most important contribution there?
In terms of the current research that we work now, like in our lab, I think the most important part is creation of a framework that can be used for controlling different types of robots. And this framework could be easily adapted for different types like of operation, different types of collecting data. And of course, with this framework, we can collect huge and diverse data sets from robotic manipulations, which is super useful in order to make autonomous systems. Because now, like mostly autonomous robotic systems conduct some not complex tasks that could be like easily automated. But if we have some complex environment with a lot of obstacles, a lot of different objects, we need somehow to like teach the robot to recognize everything and to handle these objects with appropriate force levels, for example, in order not to destroy it. And to teach this robot, it could be effectively used like simulated environments. That was like a part of my work.
Okay, thank you very much. I'm satisfied also. Professor Chen, you had possibly another questions.
No. Yeah, I think
That's
my
right.
question we already addressed. Yeah,
Okay,
by
good.
other.
Thank you very much. We'll now go to the audience outside. Anybody online, or I see Ivan Kalinov there, and others. Do you have any questions? Okay, please come. No, but come to the microphone.
Okay, thank you, Daria, for your presentation. I just want to ask you, where do you think like the application of these devices would be more have more perspective in case we want to go to investors, for example? Is it in gaming or medical robotics, or where exactly? And thank you.
Thank you for your question. Of course, gaming seems like a most appropriate area for implementing haptic technologies, as like every year we have a huge increase in the supply of VR helmets and different entertainment softwares. But I think these devices also could be effective in different rehabilitation systems with the use of virtual reality. So, for example, when the user has lost some perceptions of different parts, for example, of the hand, we can create a VR environment where the user can see that something touching the appropriate area, and at the same time we will stimulate this area, and maybe it will be possible to reconstruct some nervous system in order to rehabilitate the person. I think it's a super important area for research.
Okay, thank you very much. Ivan, I thought you had a question. Did you?
No, sorry, I have no question.
Okay. Good, thank you.
I see all thesis a long time ago, and all the versions that Daria have provided there.
Okay, very good. Nice to see you here. All right, so I think it's time now to go to the supervisor.
Thank you. So first of all, I would like to express my gratitude to all committee members. First of all, international committee members, to Professor Chen, who is famous in the robot control and robot teaching, and Professor Jean, who was also the postdoctoral researcher in MIT. Now they're doing an impressive project in the human computer interaction field. All committee members, including the chair, Professor Kliman, Tatiana Podlachikova, Professor Somov, for their valuable contribution during the process of evaluation and improvement of the thesis of the Daria. So I would like to say that, first of all, the topic of this research is very important. Nowadays, we have a boom of VR technologies, and on the market, we finally, after many years of technology development, starting from the first VR headset, now we have affordable, high precision, high quality rendering of VR environment with such technology like Oculus Quest 3 and Apple Vision Pro, which is first special computer ever designed in our human history. So, however, still there is a big gap about the immersion in this environment because we are missing REST channels. First of all, it's a haptic channel. If you cannot touch the environment, you cannot perceive the object, still we are not have the same feelings that in real life. Therefore, recently there are lots of big grants from, for example, Horizon 2020, Edge Reality for ultrasound haptic display, multi-touch, multimodal haptics with touch devices, touchless. Horizon 2020 is a novel haptic technologies leveraging the neurocognitive model and AI. And the contribution of Daria to this field is difficult to underestimate. Her first work was presented at the main conference as a World Haptics, is a major conference in the field in Tokyo, where she presented the work on the Delta Touch, which is a world first 3D display for presenting the realistic haptic sensation on the palm on the user. Also, she did excellent quality papers. Overall, 11 papers are indexed in Scopus, and she has a Hirsch index as high as 6 in Scopus. She also the first author of the major journal on haptics, which is IEEE Transactions on Haptics, and also co-author of Q1 paper, Journal of Robotics and Automation. So what is importance in her contribution? So she did amazing work in the area of the mechatronics design of the wearable haptic technology, and she spent a lot of time to achieve the low light display with a high quality perception, and did a lot of experiment user study to understand which tactile patterns actually works better. Also, she contributed a lot in the development of the 3D environment, making the digital twin of 6 degrees of freedom robots. And for sure, she did a user study which proved the effectiveness of using haptic feedback for the telemanipulation of robots. It's worth noting that she contributed to another project of our lab, such as Aero VR project, which is her first work based for aerial manipulation using VR and haptics of the Dr. Grigory Yashin, and she contributed also to the research of Dr. Ivan Kalinov with a project Where We Are for automation of warehouses using virtual reality. So importantly, Daria did a lot of work to the lecture on VR, AR, and haptics. And we started this lecture 4 years ago in Skoltech, and we did a lot of good project with a student, which led to even high quality papers in A-star level conferences. So overall, I would like to say that this research maintains the high-level standards in the field of haptics and virtual reality. I also would like to express my gratitude to my former academic advisor, who is one of the pioneers in the field of haptics and virtual reality, Professor Susumu Tachi. And definitely, Daria deserves the highest grade for her work, and I wish her to continue do important valuable research in the field of this area. One of the key applications that we didn't mention today yet is definitely the surgery. So teaching of the doctors is one of the important trend right now to achieve the high quality medical service in the future. So, and for sure, we're now working in the lab on the imitation learning, and the part of the Daria will be very valuable in the field of artificial intelligent robotics. Thank you so much for your excellent work, devotion to your work, and maintaining the high quality standard in this area.
Okay, thank you very much. I think we've now ready to go. We'll ask everyone that's not in the jury to leave the room for deliberation of the jury, and we will call you back soon. Dimitri, you have to leave. Well, Daria, we congratulate you. You even was accepted as is, and you're granted the degree of PhD. So thank you.
So first of all, I want to thank Skoltech for giving me such unique opportunity to study and work in the high-level university and conduct such super cool study. And I want to thank all of my laboratory and team that I was happy to work with during all this long way. It was not super easy sometimes to proceed with the different stuff that was related to publishing papers, trying to make everything working. But it was super interesting journey. And I hope that I will remember this for all my further life. Thank you.